Example 11, we're going to examine tuning the between operator. So we have information about our indexes. So on the customers table, we have a customer country state city index. It's made of composite index made of multiple columns. Okay, so the columns it's made up of the country ID, the customer state province, and the customer city. Okay, and then we're going to do a query on the customer table. Okay, and what we're interested in is customer ID between 52788 as a country code and country code 52790. We're looking at a range between it. Okay, and then finally, we're looking for the customer state province, but we're looking for the provinces or states that begin with W. We put a wildcard at the end. If the range is small enough, it's possible to use an index for this. And if we had the appropriate index, we could use an index for this. So we have an index that's made up of all three things. When it goes and processes the query, takes a look at the different options to access the data. In this case, it decided generally to do a full table scan. So we have some examples of different ways to try to optimize this particular query. So we have some SQL to have a look at, what they're going to try out in this example. So we have three flavors of this query that we're going to try out. One is we have the original query. They just want to show you what it looked like. So these were the original predicates, country ID between that we showed in the board and this one, just to confirm when they ran it, it actually did the full table scan as we noted in the slides. Then we're going to have a look at trying to force it to use our index. Once again, we placed a hint on it and said, optimizer, if at all possible, use this. So it will try to use this index, and we want to see how it compares to the execution plan and the general performance metrics, in particular the number of blocks we have to touch in memory. And then finally, we have another variation of it, okay, where we go in, it has the customer city index, but now we change the range to an in list, okay, with three values of it, okay. And we'll see if changing it from a between operator to the in list, so something you can control as you're writing your SQL, made a difference in how the optimizer does it. And was it an improvement? Until we actually test it, we don't know for sure whether it was an improvement. Now sometimes you can get a general indication by having a look at just the elapsed time to process it, assuming the load is about the same on the system. But a better idea is to look at the execution plan and look at the execution statistics and see how many logical blocks it ended up having to touch as the proof of the pudding. So let's look at some output for this. We'll open up the display, and we have our three queries. First one was the original one. In this case, it had to touch 1532 blocks in memory. The more we touch in memory, even though it could be buffered in memory, can save us some IOs, we still have to use CPU cycles to touch the individual blocks, okay? And that's what it took as doing this as a full table scan on the customer's table with our 55,500 rows that we actually have out there. And in this case, it returns a subset of the rows, 1125. Then when we forced it to use the index, customer country city state index, okay, it reduced the number of blocks it had to touch slightly from 1532 to 1240 to return the same amount of data. All things being equal, go with the smaller number of logical blocks. you can touch to solve the query. And in this case, it did an index skip scan on it to access the index. And we'll have a look at the details of the index skip scan, but at the bottom of the tree, we don't have to look at every index leaf node. We can skip over some of them, provided by the information we know about the predicates. Usually, if we use an index prior on very old versions of Oracle, back in version 8, if we skip the leading index on an index, it wouldn't do it. If we skip it now, it can do a skip scan on it. So what it did is really use that index to process the INS range of the skip scanning process. Okay, and we'll talk about the skip scanning a little more detailed as we get into accesses. What we're interested in noting, because it could use the index, we reduced the amount of data we had to touch in memory. The second variation, okay, was to change it to an IN list, which is just the way we wrote the code. It returns the same number of rows, but it used the index, but now we could reduce the data further by using the index. We had to touch a few less blocks. It translated to less CPU time and less elapsed time overall for the execution. We go with a smaller number. Out of the three of them, this was the best choice. We had to do two things. One, we had to restate the query. If the IN list becomes very long, we'll talk about the IN list processing later on in details, but basically we take the index and probe it once for this value, probe it another time for this one, and probe it. Then the three of them, rows, if we get maximum of 3 row IDs, they all solve the query. And then we have to apply this predicate afterwards without an index. The second thing we had to do is we had to force it to use the index. So sometimes it takes a hint to get it. Great for testing. And in this case, we noticed that they did an IN list iteration, which means they probed this index 3 times with 3 distinct values that we had in the index. If we could rewrite this as an OR condition, but then it wouldn't use the index if it's expressed as an OR condition in a lot of cases. So this turned out to be a nice little variation that took a combination of rewriting the statement plus using a hint. So back to the next example. Okay, in example 12, we're going to have a look at tuning joins. Okay, and we're going to have a look at the joins. So we have a little careful, and we have some general rules that tend to be good for help guiding the writing of the SQL statements as you're writing your SQL statements. One is avoid full table scans if there's a more efficient access path by using an index. If we can get the data cheaper using the index, we'd like to avoid a full table scan if we can, especially if we're looking for small subsets of the data to join together. Avoid using an index that would fetch 10,000 rows from the driving table if you could use another index that would return 1,000, which quite often means change the driving table so we use the table with the best driving condition, a predicate that will reduce the rows the most. In fact, the one it likes the best is a predicate on a unique index that has a single value. That reduces one side that could be a loop when we join tables together to either 1 iteration or 0 if there's no values returned. It really likes using that for the driving table if it can. Okay. Also, we'd like to choose the join order so that it joins the fewest rows to tables first, okay, and join the bigger tables later. What we'd like to do is start, if we have multiple tables, 3 or 4 we're going to join, and 2 of them are large and 2 of them are small. If we join the 2 small ones together, we get a relatively small result table. Two small things give me a relatively small result table. If we join the big ones together, they're already big. Joining two big ones gives me a big result table. I'm dragging that large thing around the maximum amount of time through it. So we're dragging extra rows during the processing. So it generally likes to join the smallest tables first. And one of the decisions the optimizer looks at as part of optimizing a join normally is a join order. So we have a little query to illustrate this, okay, as we're processing it, okay. We got three tables, table A, table B, table C. We give them three aliases, A, B, and C, okay. And then we have some join conditions, okay. We have some filters on three of the columns. A column, we're looking for things between 100 and 200. This makes the assumptions that A column is a numeric value. Then column B, we're looking for things between 10,000 and 20,000. This is a narrower scope generally than this. Now, once again, it could depend on your data, but in this case, it's generally true. If these are all integers and they were fully populated as integers between 100 and 200, 100 is less than 10,000. 10,000 to 20,000 is 10,000 values. If they're real numbers, the data may be skewed, so be careful. But the assumption here is that this is a narrower range than this is. And the same thing is true B. It's a wider range on C, on its column 1, that it is on A's column 1, okay? So generally, if we could use this as a driving column, and we have an index on A column 1, and we could convince it to use it, it would reduce the data the most. We could do a range scan on this instead of doing a full table scan. And though these are three filters, these three items are basically three filters on individual columns in the three tables that the optimizer can use to see if it can use an index to reduce the data. These are the join conditions. We're going to do an equal join between three tables. We're joining A to B as an equal join on key 1, and we're doing A to C as an equal join on key 2 to equal join the three tables together. So it will consider join order and the filters to figure out what is the best access path for these, okay? So on these, they have some examples in their notes and they just discuss it, so we'll have a quick look at the notes. So join order can have a significant impact. That's why we made a little discussion of it above. The main objective of SQL tuning is to avoid the performing unnecessary work to access rows that do not affect the results. This leads to the three general rules we listed in the slide. Okay, so this actually shows how to tune it. Choose the driving table and the driving index. There are three conditions on this one, okay, that are filters. The first two I showed you. These two up here are basically the filters on the data. Then we have the join conditions, okay. The filter conditions dominate the choice of the driving table and indexes. In general, the driving table is the one that contains the best filter that eliminate the highest percentage of the table. Return, pass through the lowest number of rows. Reduce the data as much as possible, as early as possible in the SQL processing. Thus, the ranges between 10 to 20 is considered narrow than between 10,000 and 20,000. Assuming they were fully populated with integers, that would be true, okay? So in that case, it means that table A is the table, the one that has the best condition would be the best one to use as the driving table, okay? With the nested loops, the joins all happen through an index join. The indexes on the primary and foreign keys used to connect the tables to an earlier table in the join tree. Rarely do you use an index on a non-join condition except for the driving table. It uses it on that, an index on it to reduce the data, because then it will use the remaining data to join to the next table in the order. And it really knows how to join two tables at a time. If we join three, we do them as two individual joins. Join the first two, create a result set, join the result set with the third table. Okay, thus table A is chosen as the driving table because we have an index on the column that reduces A the most, gives us the least data to feed into the join. Use the index on key 1 and key 2 if they exist to drive between the join of A to B. Okay. Choose the best join order to drive the best unused filters earliest. You can reduce the work of following joins by first joining the table with the best still unused filters. So if the column B had a more restrictive than column C, which it doesn't, they were actually considered the same. But if there were a different range and one of them was more restrictive, then we pick it as the second one in the join order. Okay, so it will look at different permutations and cost them all out within the second we give the optimizer to do normal parsing and decide which is the best choice. If you don't want it to look at different join orders, there are actually two hints that prevent it. One is the ordered hint. It says use the tables in the order that they're actually specified on the from clause. Don't look at different combinations. Okay, and the second one was use the star hint, which is a optimization for star schemas for data warehousing. And both of those changes its decisions about looking at different join orders. The third thing that influences it, remember that outer joins have to be done in a particular order. It actually stops it from looking at some join orders. Because if we do them in the wrong order, we just don't return the correct data. And correctness takes a higher priority than performance, as the performance is an incorrect answer. Okay. Now, example 13, we're going to test for the existence of rows. Okay. We want to know, in this case, we have a little query that's going to check only if there are customers who purchased a specific product, okay, from all the customers that have a credit limit greater than 10,000. So somebody has a great credit limit and he's purchased a certain product. Okay, so that's what we're looking for in this case. So those marketing people like to do all sorts of questions like this. So we form this as a query. We're selecting account into, and this was just an example to show you up to now we've been looking at queries that were just executed directly in SQL+. Your queries can be wrapped in PLSQL code, and the optimizer still basically processes them the same. It goes in and looks at them and accesses the data the same. So this was a little example. We wrapped this in a PLSQL block, opened our own cursor. We're going to return all the rows into our catcher, our array to catch the count of rows into a integer count value to count them. And we're joining the sales tables to the customer table. We're doing an equal join between this. This is the join condition. The rest of these are filters. Okay. Okay. So we want to know a particular product. They're passing in the product as a variable to this PLSQL block. It's going to be the product ID. It's a host variable here. Okay, and we're going to have, so we're looking for a particular product, and the credit limit we hard-coded at 10,000. Okay, then we're checking to see if we got a row returned or not, one or more rows. If we didn't get any rows returned, there's nothing to work with. If not, we would just process the rows one at a time using a cursor for loop. Okay. So when it went to access this query, it chose to do a hash join. Okay, it did a full table access of the customers table, and it did a range scan on the sales table. Okay, based on the sales primary key, which is the customer ID. It was able to reduce the set of customers, okay, based on our additional conditions that we have here, okay. So it cost us a certain amount to do that. There are some other variations we can look at, whoops, with these, and we have an example, a set of examples to look at. This original query and the details of how it processed it, and a couple of rewrites trying the exist operator. And these are things you can influence with your code as a developer. You're writing the code. Okay, this is your code, this influence. So let's look at these examples. In 13, we'll look at their 3 examples of their code. So we have the first variation we're looking for, and in this case, they didn't do it in a PLSQL because we just wanted to write it as a script. We hard-coded the product ID as 120, and we're looking for the limit. So it was a little slightly different example, but it's going to process the SQL, except we didn't pass in. We could have did it as a bind variable and got you to fill it in, but it simplified executing it. And we'll have a look at that. Then we rewrote it using the exists. Okay, all we need to determine is one customer, okay, with that credit limit, okay, that meets our inner query. There's one existing row, and then we have a match for this particular product, okay. So we're using a exist qualifier to do it. And there's 2 ways when we changed it from a join of the sales to the customers. We can use the sales on the outer query, and we can use the customers on the inner query. The other way is just to flip them around and use the customers on the outer query and use the sales on the inner query, the exist portion. And we'll have a look at all 3, and these are just different ways of writing the same statement, different ways without getting a hint and taking a look at the performance. So how you write your code can make a difference in reality. So let's look at the output for these. Okay, so we'll have a look at the 3 of them. The first one, we're having a look at our first version. To process this, we had to touch 1561 blocks in memory to return the 1 row. We were just looking at 1 product, and we wanted to know what was the count of customers that were that had greater than 10,000 that had this product. And that cost us 1561 blocks we had to touch in memory. We did it as a hash join, as we showed on the slide. Did a full table scan of customers and did an index range scan on the sales primary key to do the hash join. Okay, doing it the second way, we'll just move it up to the top so it's easier to read. We rewrote the join to an exist qualifier and used the customer on the exist part, the sales on the outer part. That saw a nice reduction, substantial reduction in the processing. We went from 1561 that we had to touch down to 45 blocks. Much less CPU time. We saw a nice reduction in the CPU and the elapsed time, which were the same. That's the best case scenario. CPU is highly available. And this had to cost us something, but it was less than 1/100th of a second below our ability to measure it with this tool. Then it did that as a nested loops. And you find that it has this count key because all we want to do is return 1 row from each of them that gives us the indication, the count of the customers. So we used the stop key, but we used nested loop, and now we were able to use 2 sets of indexes, 1 in each side of the nested loop. that reduced the data substantially. Did restating it by flipping what was used on the outer query and what was used on the inner query around, putting the customers in the outer and putting the sales, did it change it? Yes, it further reduced it. Okay, went from 45 blocks we had to touch in memory down to 20. The better one is the one that touched blocks. We don't see any difference because we were already below our CPU, but if we scaled up to larger values, then we might see a difference in CPU time, okay, and execute it. And this did it as a nested loop, as a semi-join, doing a full table scan on the customers, which was on the outer query, okay, and then doing a range scan when we processed the inner query for the sales table. We were able to take advantage of an index on the sales table to do this join. So pick the one with the lowest number of logical blocks we're having a look at. Next up is a little example of looking at the like, okay. Now this I find a really interesting technique. Once again, it's restating the query the way we wrote it, and I think to a certain extent it's a little bit of an interesting programming trick. It's realizing something about the data and how we could represent the data differently, okay? And it's actually really interesting. If we were using a like clause with the where string at the beginning of the like clause, if we had put the wildcard at the end over here, then we could use an index to solve this. It would be a non-unique index on whatever the string is, and we could use the index to actually solve it. By putting it at the beginning, it removes the possibility of using an index normally. But we have an interesting way to doing it. So what we want to show you, if you have the customer's last name index as a regular balanced tree index on the last name, okay, and then we do with the wildcard in front, darn it, it couldn't use the index. How disappointing. We had to do a full table scan. But we would actually like to see it using the index. Is there a way of rewriting the query so it can use the index? And sure enough, there turns out to be, okay? And this is an interesting trick. We have the output for this, where we might have a look at. I just wanted to make sure we did. Okay, so 14, we can have a look at the queries, their original and their new query. Okay, so we're dropping the customer last index, okay, and we're just going to make sure we don't have an index on it. Then we could create a regular index on it. It doesn't matter whether we have the customers, and this was the new index we're going to create in the later parts. They want to make this repeatable. We got rid of the old index, the special one we created. We just left the original index on customer last name, but because of the wildcard, we don't expect to use it. We're going to confirm that. And then we do an interesting process. There is in SQL Plus a whole group of functions. One of them is a reverse function. It will store a string backwards. It just reverses the string. If I got ABC, it will return CBA as a string. Really simple processing. But I can actually take advantage of that to use this to improve the performance of this query potentially. What I'm going to do is create a function-based index. It just looks like a regular index, but instead of putting it on the last name column directly, I put it on the reverse function applied to the customer's last name column, which makes it a function-based index. By doing that, the data in the index is stored backwards. What was ABC is now stored as CBA, just in the index, not in the data in the table, just in the index. And then when I write the query, I can apply the reverse function to the data to allow it to do the index. And this is the tricky part. Now we reverse the string we were looking for. We were looking for something ending in ing, reverse the ing to GNI, and then put the wildcard at the end. It can use maybe this function-based index. The proof is seeing it actually working. Okay, so let's take a look at the output of this. Okay, first one, we have the regular index. Couldn't use the index, it ended up doing a full table scan on it. We confirm it down here, so as we expected. But now we add the index, rewrite the statement, so you control the code. If you're developing the application, depending on your organization, some organizations, the developers create the indexes. Some organizations, development DBAs would. But if you create your own indexes, you can create your own function-based indexes for this. And when we did it as a full table scan, we had to touch 1501 blocks in memory. Now, when we reduce the number of blocks we access to return the same data, because now it can do a range scan on the function-based index. Less data, better query, and it performs better. And we also saw a nice reduction in the CPU time. Sometimes we don't see that much, but then some of these we do see a nice reduction. All of these right now are running less than the second we expect OLTP type applications to run.